Okay, so this homework was really great because it made you think hard and have to kind of reason through some stuff. This got you to kind of work on how to graph the derivative given a graph. Now, of course, your final graph is going to be approximate because we don't know the exact slopes, but we can come up with pretty good estimates, and also it should be off in a way. Oh man, are you kidding me? It was perfectly fine right before this. I didn't move anything. Jesus. Let's see what changed. All right. So we didn't really need our limit definition of the derivative. We just had that little reminder there. But this was our function that they gave us, and they asked you various questions. When is my slope increasing? When is my slope decreasing? When is the slope zero? Things like that. When can I not take the derivative? So remember, derivative is the slope of the tangent line. So when we're looking at our graph, to graph our derivative, we want to be thinking slope. What's the slope along these points? Okay, so let's just go through this. Are there any values for which the derivative does not exist? So I hear no and I hear yes. How do we know if a derivative does not exist? What are our four situations? Both of you want.
Cusp.
Cusp. Good. What else do we have? Corner. Vertical tangent and? Yeah, sometimes discontinuity, right? Okay, now remember that our cusp and corner are pretty much interchangeable. I looked into the book to see kind of the defining difference, and they said that a corner is where our left-hand slope and our right-hand slope are different values. Whereas a cusp is when we have our slopes are going toward infinity. So basically the slopes are getting forever larger in the positive direction or forever larger in the negative direction. And again, we talked about that if our slopes are getting bigger and bigger and bigger, then that means my line is becoming a vertical tangent. Or if my slopes are getting larger and larger in the negative direction, again, it's becoming that vertical tangent. Okay, so, but for this one, I would say that we have, like this guy here, kind of looks like a mixture of a corner and a cusp. So again, those are used interchangeably. If it's corner and you call it a cusp, I'm okay with that, and vice versa. So here's one in which kind of looks like corner because we have an actual derivative on the left and cusp-ish on the right because it's, again, my slope is getting larger and larger toward that infinity. In other words, it's that sharp point, right? It gives me some type of sharp point. I cannot draw the derivative of a tangent line at it. What is the slope of that? We don't have anything to define that. Do we have another point similar to this? Yeah, good. Also, did I have any vertical tangents happening? No. And it's continuous, so we're good here. All right. So that was what? -2 and 2. All right. Questions on that first part? Ideally, we were good there. We should have into that.
Is there any situation where like it looks like a cusp, but it's not?
Not that I can think of. Pretty much if it comes to a sharp point.
So we should definitely expect sharp points to see it.
Yeah. Yeah. I mean,
are we ever going to be expected to find a cusp from the function itself?
like it's not graphed for you.
Yeah.
It would probably be coming from some type of piecewise function if it were like that. So you might have to graph the piecewise function and see, like for this, it would have been a piecewise function where it had y equals some line and then an upside down parabola. In that case, perhaps, but you would probably first draw the graph to see it. All right. So B, are there any values x for which our derivative is 0? Again, derivative, we're talking about slope. So is there any point in time along my graph where when I draw the slope at that point it is 0? What do you guys think? At x equals 0. And it just so happens to be that it's at x equals 0. But when we take a look at this, if I draw in my little my little tangent, what type of line do I have here? A horizontal line, and the slope in a horizontal line is 0. So in order for my slope to be 0, that tangent should be a horizontal line. As I kind of just, again, to help you out, you can always just use your pencil to kind of represent the slopes. Here we have that issue. So again, positive, it's getting smaller, 0. Now we're going negatives, bigger, issue, and then positives. All right. Now our next question. So this particular function has an interval on which its derivative is constant. What is this interval? So again, the derivative, so again, we're talking about slope. So where, whoops, supposed to be here, slope. So where on my graph is the slope the same for a chunk of time? Oh. Yeah, along this chunk here. Now, we were talking about this last class. We didn't really have an indicator as to whether these lines are going on for forever or if it's stopping there. For simplicity, I'm just going to go ahead and say that they're going on forever so we don't have to guess what that value is. But for this chunk, the slope is the same the entire time. Maybe the -2. Now, if you said -4 to -2, that would be fine, because again, we didn't know if it was going on. And I do not include that value of -2, because again, I cannot take the slope at that point. What is the slope there? -2. It goes up 4 to the left 2, which is back down to -2. So my slope was -2. Plain old algebra there. What does the derivative function look like there? And we estimate the slope on that. So we're looking just at what our slope looks like at this point. Now we said that the slope is -2, and for this entire interval, the slope is the same. So if I were to graph those values, all right, so at -2, again, we know we don't have that actual value, but it's going to be getting towards that too. Okay, at -3, my slope is still that -2. At -4, my slope is still that -2. So it's that same slope that whole time. And if my slope is constant, my derivative graph, which is my slope, means I should have constant value along. So you should have had just a straight horizontal line at -2 for that left chunk of my graph, because it's the same slope all along. Now we're just going to graph the left piece for now, since that's all we've investigated so far. But questions on that? All right. Now, in which interval or intervals is my slope positive? A derivative slope. So when is my slope positive? And then on C, it asks when it's negative. So we'll just go through our graph from left to right and write down our different intervals. Here, is it positive or negative? Negative. That part we already figured out. All right. Now, once we come along after -2, is this positive or negative? Positive. So that's what? -2 to where? Good. 0. And we're not going to include that 0, because the slope at 0 is 0, so that's neither negative nor positive. All right, now once we go past there, is this positive or negative? Negative. Good. Our slope is, if we were to draw my tangent at any point in time along there, it's a negative slope. So that's from 0 to 2. And then we've got this part, positive or negative? Positive again. If I draw any of my tangents, take your pencil and move it along. That gives you your little slopes. Positive. So we'll just say 2. So we should have been able to get those intervals because we're just simply looking at the slope of a graph, right? We're just taking a look at my graph, identifying the slopes along there, whether they're positive. Any questions on those? Is there more to do? Again, sketch a graph with the derivative on those intervals. So see here, talking about the negatives. Now this is kind of the trickier part here. I think the middle part of my derivative, this part here, ends up being the trickiest part. So we have a positive slope, negative slope, and we know at 0 the slope is 0. Okay? I'm just going to go ahead and continue it on my graph up here, just to make it a little bit easier. All right. So we know that my slope is 0 at 0, so let's go and just plot that dot. Is 0 at 0. And again, from -2 to 0, it's positive. So we should be above the y-axis because it's positive. So let's take a look at this. I start off, I know we don't know exactly our slope, but what would you guys say is a good approximation of this slope pretty far to the left? 1? That sounds reasonable to me. And then as I go, are we getting smaller or larger? Smaller. And we can see that that slope is getting closer and closer to a slope of 0. So I start off somewhere around 1, and then my slopes are getting smaller, and eventually it hits 0 there. Now, again, I'm going to have an open circle because we don't have the derivative at -2. But we know that it's approximately about 1 when we get there. And then again, my slopes are getting smaller and smaller and closer to 0. So thus, we should have it starts off about 1, and then they're getting smaller to 0. Is it a straight line? I don't know. Is it a slight curve? I don't know. But we have the approximate idea. It's positive, starts off about +1, and by the time we get to x equal to 0, it should be 0. And it stays positive that whole time. Questions on this? So when I look at this interval here, starting at -2, if I give a good guess as to what my slope is there, somewhere around 1, and maybe 2, might be a little more than 2, might be 1.5, but we're getting an approximate. We don't know the exact slope. We can't know it from right here. We can't know it at all because they didn't even give us a function, but we're just getting an approximation there. Other questions on that part?
So when it says graph the derivative, whatever the derivative is, that's the point that you take?
Mm-hmm. Yep. So your derivative is it's saying at x, what is my slope there? This next x, what is my slope there? So we're basically finding our slopes. If we were to create a chart, my y values are the slopes of my original graph. Does that make sense?
Yes, you don't draw the actual slope. The point is
the point value is the slope value. Yep. Other questions so far? Okay. Now I just realized we actually did the positive value, so it looks like we're actually doing the whole graph, but that's okay. All right, so then we have from 0 to 2, our slope was negative. So we know that we should be below the y-axis here. From 0 to 2, I should be below my y-axis. And if we look starting off, is this a small or large negative slope? It's pretty small, right? Now as I go, are my slopes getting larger negative values or smaller negative values? Larger negative. And again, let's give an approximation of right here about, what do you think your slope is? -1 sounds reasonable. So at 2, again, we're going to have that hole because we don't have a derivative there. We don't have an exact slope. But we know it as we get really close. It's about -1. So at 2, again, it's going to be a hole, but we know it's about -1. And again, we said there's small negative values, and then they get to be larger and larger negative values. And again, so small negative values going to be larger and larger negatives. Again, I don't know it's a straight line. It could be slightly curved, but the general idea is that we are positive larger to smaller positive at 0, and then small negative to larger negative there.
None of that
At prime of x will not be continuous. And we know that because if it's not differential at those 2 points, that means it's not continuous at those 2 points. Other questions so far? Okay. And then we've got our last term. Alright, so then we have 2, 1 to infinity, and we said that this slope is positive, right? Now, again, are we starting off with, or actually, let's say just approximately, about what would my slope be here? Just give an approximate guess. I mean, I would say anywhere from like 1/2 to 2, somewhere around there. Again, we're just getting approximates. We have positive. Now, are my positive values getting larger or small? Again, larger. And it's positive this entire time, which means I need to be above my x-axis because I need to have positive y values. So we should have some type of discounting. What's my discounting going to be? A definite jump. Because we switched from negative slope to positive slope without any, we didn't go to 0 in between. All right. So let's see, we're at 2. Again, it's going to be an open circle because there's not an actual derivative there. And it's somewhere in this positive region. And it gets larger. So we're going to be getting larger values here. Again, that could be a straight line. Maybe it's a slightly curved line. Not completely sure. But we know it's Starts off as a smaller positive value, but then it increases and gets to be larger pretty fast. Okay, so it might be that Hart's curve because it gets to be large fast, but we're not completely sure. All right, so I'm going to just go ahead and draw that down here a little bit better. But this is essentially our graph. We've got that constant slope coming from infinity to -2. We have a positive slope, zero slope at 0, negative slope. And again, it starts off with a bigger positive and gets smaller, and likewise with our negatives. And then it doesn't hit a slope of 0, so we could expect at these 2 points where we have those jumps, that's not continuous, we know that means we can't take the derivative, right? The derivative is not continuous, which means the original function doesn't have a derivative. Also, the derivative isn't even defined at that point. All right, and then we have positive slope again. Does anyone happen to get the graph completely right?
Why are you to the point?
Why is what?
Because 0 is a point because it's
At 0, my slope is 0. If I draw in a little tangent there, it's a horizontal line, the slope of that line is 0.
how do we
If we draw in a tangent,
like without like just by looking at the graph, you just look at the graph or is it like a map?
no, you're just looking at the graph, so I could even go right here and say I have slope of 0 right here and slope of 0 right here. As I draw my little slopes, it's going to be whenever it's kind of a peak or a valley of a graph. That's actually is what it is. When I have that vertical tangent, so if you take your pencil and just kind of outline along it, that's mimicking your slope of the line, or it's mimicking the little tangents. So like right now I can say positive slope, positive, positive, we just got a horizontal tangent. Horizontal lines have a slope of 0. Then as I continue to trace along though, now we have negative slopes, negative slopes, negative slopes, negative slopes. And now again, once again, we get that horizontal line tangent, slope of the horizontal line 0, and now we're going to positive slopes.
So if that was our graph and it asked where the derivative was 0, you just do whatever x value that b is over.
Those two exercises. Yep. Other questions? So then let's see how we did on our graph match. It's not going to let me scroll. What's that? Yeah, but this is my second page. I was trying to scroll over. All right. Let's just see how you get 6. What did you guys get for this first one? B. Good. This guy? D. This one? Good. B, D, and A. And we'll take a look at these. How about here? Good. C, and that's this one's E. Now, when we're going through these, let's go back to this. When we're going through these graph matches, you can look at your original, think of your slopes and see which derivative matches that, or look at your derivative and think what type. So these are negative slopes, positive slopes. So on my original graph, I should have negative slope, positive slope. I kind of think it's easier to start off with your original. Talk about what your slopes are, and then look for the graph that matches that. Key things to do. Decide when is your slope positive, and what interval is it positive. Is it going from small to big, or big to small? Which direction is it going? Do the same thing with your negative slopes. Identify when is my slope negative. And again, is it going from a small negative number to a big negative number, or vice versa? Because that'll let me know. For my derivative graph, should I be starting off with a large negative number and going to smaller, or should I be starting off with a smaller negative number and going to a larger? And then the other big thing is, when is my slope 0? So using that can help you identify these different So for my first one here, what is my slope along the entire time? It's positive, right? We've got it's positive. It's not super steep, so +1, +2, something like that. Does my slope ever change? No. So I should have the same slope value. My slope here is constant. It's a positive, and it stays the same. So I should have the same positive value the entire time. If I look at my graph choices, here my slopes are different. Here my values are different, meaning the slopes were different. Here my value is the same, so the slope is the same. Changes, changes, same for some, changes. And F is also the same. So that brings me down to B and F. Now at F we see we have a hole there, which means my derivative is not continuous. The derivative is not even defined there. And if the derivative is not defined there, that means my function didn't have a derivative there. Well, can I have a derivative at 0 for this guy? Yeah. My derivative here is the same as it was for everything else. So that's how we know it's B. So then we can use a similar technique for the rest of them as well. I like to start off with identifying when it's 0. So for D, I have that it is 0 at x equal to 0. So I should expect to see on my graphs, I want it to be 0 at 0. So it's not A, it's not B, it could be C, it could be D, can't be E because we have that jump there. So I've already eliminated 4 options, and I'm down to just C and D. So then again, look to C. How are my slopes changing? Here, my slope is positive, and then it changes to be a negative slope. So I should expect on my derivative graph to start off above, from -3 to 0, start above my x-axis, and then change to being below it. And without even considering if it's small or big, we can immediately then choose D from here. C, the slope is positive the whole time. Because my y values are positive, that means the original function's slope is positive. D, it has the values change from positive to negative, so the slope changed from positive to negative. So that allows us to do D. And then similar thing with A here. First of all, do I have the derivative at x equal to 0? No, it's that corner. So I have it's not differentiable, so I should have it's not even defined at that point, which would give me A, E, or F. So again, these are just kind of the different techniques. Is look to see. All right, well here it is a negative slope, and it's the same negative slope. We have it is not differentiable here, so we should have some type of discontinuity on our graph, on our slope graph. Notice that discontinuity on our slope graph, not the original. Then here my slope is positive, and it's again the same positive value. So we should expect to see a straight line because it's the same value, some type of jump, and same value again. So that gives us A here. Same negative value, discontinuity, same positive. And with these three, again, this is the same positive slope that whole time. We have it's discontinuous at 0, and then again we have another positive slope, and it's the same the entire time. So we'll be looking for that. C, I have here, it's a positive slope. I start off with a large positive, and then it goes to a small positive. So I have from big to small. My slope at 0 is 0. And then again, I still have a positive slope here, but now I go from a small positive to a big positive. And then with E, we've got that corner cusp looking thing, so we have that discontinuity. My derivative will not be defined there. Again, positive slope, it stays the same positive slope for that entire interval. Here, positive slope, but it changes from a small slope to a big slope. So I should expect to see on my graph, I can even come up with the graph just with this information. Same positive slope, maybe about 1. So it's going to say here. It's discontinuous, or it's not differentiable, so thus I'm not going to have it defined there. And then again, positive slope, small to big. So it looks like it gets pretty close to 0. So small to big. It might be like this, it might be like this, but small positives to big. Questions on those and kind of the techniques of the techniques?
Will we ever have two graphs that could be straight lines and curved lines, and we have to choose? And since they look so
Oh, like this guy here. Like, would you have it be like this and and choose? Probably not. They would probably not do something that close. I guess you could always say it's possible, but probably wouldn't give it something like that. What you could do with that is see, this here says, so if I have a straight line, this says that the slope is increasing at the same rate, whereas this one says the slope as you go this rate increases drastically. So you could compare with your graphs which one increases more steadily and which one increases more drastically. Other questions? So we'll continue to do more with derivative graph match as we do more with derivatives, but this was kind of just to get you start thinking about how does the graph relate. Remember your original function, whatever its slope is at those different points, that's what creates your derivative graph. So think positive slope, negative slope, it's going small to big, big to small, and slope to zero. Okay, so today what we're going to be doing, that was kind of gearing up for kind of leading into today's material, is we're going to be learning about derivative rules for polynomials. Now, the way that I'm doing it this year, the way it's structured, is a little bit different than some other ways that calc is structured. Traditionally, calc is structured limits, derivatives, integrals. What we're going to be doing is limits, and then you go derivatives, integrals, and polynomials. Then you move on to log, natural log, and exponential, and do derivatives, integrals with those. Then you move on to trig and do derivatives, integrals with those. So it helps us to kind of get familiar with the derivative rules with polynomials, which is really the easiest way to use the rules. And then as we get more familiar with it, we'll build with the more difficult functions. So we're going to be doing handwritten notes, and you'll find that we do handwritten notes pretty common in here. You were spoiled with Unit 1, so make sure you have pencil sharpened and erasers ready for the rest of the year. Now, you will probably want to have a highlighter or colored pencil nearby. There's some things that we're going to be doing different colors or places that you can know about. And if you ever want to use them, I've got your pencil here. They have some highlighters as well. Alright, hold on. Smartboard's gonna mess with me. Let me restart it real quick. Okay, so this is Unit 2. It's dealing with polynomials. That'll be our functions of focus. And today we're starting off with just our basic derivative rules with polynomials. So day 1 here, derivative rules. Now again, these are derivative rules that apply to find the derivative of any function, but we're looking at it specifically with polynomials. So like we're going to be learning product and quotient rule. We can do product and quotient rule even if they're not polynomials, but we're going to be using polynomials for this first one. Okay, so our first one is our constant rule. And our constant rule is pretty basic. It says that the derivative, d dx, of any constant we'll call c. So again, remember this d dx means take the derivative with respect to x. That means take the derivative. And we just went ahead and specified of this function here. So c is just some constant, 10, negative 1,000, 1.2. The derivative of any constant is 0. Now, if we stop and think about this, this makes sense. Because the constant, let's say that our constant is 5. If I think of my graph, what does a function y equal to 5 look like? Horizontal line at 5. What is my slope of any horizontal line? 0. Derivative means slope. Good. So derivative of any constant is just 0. Alright. There we go. Exciting rule number 1. Now the next one we're going to be looking at is actually our power rule. And this we're going to investigate a little bit with our calculators. Power. Alright, so this is the derivative. The function to a power. And we're going to go ahead and pull out those calculators and take a look at it. So if you have not found your calculator, find your calculator and do it.
Doesn't matter what the number is. Doesn't matter what number.
No, you don't, it doesn't matter right now for what mode we're in. General rule of thumb, though, you want to be at gradients, unless they give you your angles and degrees. Okay, let me clear out my functions here. Okay, so let's all go to our home screen. Now, you can actually use your calculator to help you find the derivative at a point. Unfortunately, you cannot plug into your calculator, find the derivative of sine of x, and it will not spit back to another function. If you think about it, on our home screen, we never have our calculator spit back a function, a variable x to us, right? It only ever spits back numbers. So let's first take a look at where this derivative notation on our calculator is. So you want to hit math, and up until now, you've probably only ever used options 1 through 5. But look at option 8. It says n deriv. That means to take the derivative at a point. Now, depending on whether you have the update or not, if you have the update, you'll have it presented to you in this nice format. If you do not have the update, then you'll see this. Okay? So I want to just go and write the notation. We'll write it down on our notes. I'm going to bring up another page just for this kind of exploration that we're doing. But so again, we go to math, and it's option 8, n derivative. This is what we're using. Now, again, on the new updates, please, I'm not as familiar with the new one because mine does not have it. D over D box. And then it says function. I think box. Now, on the old update, which says enter. So what we do is in our new update, this first box represents what variable are we talking about. So we're going to put in an x. And this box here needs to be that same variable. Okay, so we're taking the derivative with respect to x, at x equal. In our n derivative, that part comes a little bit later. Okay. Now what we put in here is my function, or whatever it is we're taking the derivative of. So let's take the derivative just for kicks and giggles. Let's set f of x be 3x minus back 3x minus. Okay. And then let's find f prime of, I don't know, give me a number. 2, that's it? Alright. Okay, so again, we can only use this to find the derivative at a specific point. It will not give me the entire function derivative, just the derivative value at 2. So what we put in here then is our variable would be x. We put in our function, which is 3x minus 10. Our variable is x, and I think it might actually fill it in for you once you put an x here. And then we're looking specifically at 2. For those of us that have the old update, you want to first put in your function, then your variable, so x, then that number that we're looking at. Okay? So again, for us, we would have, for this problem, 3x minus 10 goes in here, and 2 goes in here. And if you're using the old update, 3x minus 10, comma x, comma 2. Expansions equation. X, 3x minus 10. Yeah, see how it knows it automatically filled in that same variable for you. And we're looking at this one. And what did you guys get? Okay. So then what that did is it just told me the derivative of my function at 2 is 3. And we now know that the derivative is 3. Which means if I look at this function, it's a y-intercept of negative 10 and a slope of 3, right? 1, 2, 3, 1, looks like this. What is my slope at 2? Oh, 3, because that's the slope of the entire line, so that makes sense. Alright, so again, you have to put in your variable that you're taking with respect to, the function, and then the number you're looking at. Old update, function, variable, number you're looking at. Questions on how to use that? Okay. Now, that's great, it's telling us the derivative at a single point, but like I said, we cannot have it spit back the function to us. But we're going to outsmart the calculator a little bit, and we're going to use our graphing mechanism here to help us kind of see at least what the graph of the derivative looks like. Alright, so again, it will not spit back to the function, but we can at least see what the graph looks like. So let's start off with just x. We're going to compare this actually a bit. So we're going to take a look at f of x equal to x. What is its function? What is its derivative function? Then we're going to take a look at x squared. We'll take a look at x cubed and x squared. Okay, so we're going to start off with just x. Now, if I look at my graph here, we can probably figure out the derivative. What is my derivative? What is the slope all along here? 1. It's the same slope of 1, right? Let's see if we're right. Okay, so how we're going to outsmart the calculator is in our second function here, we want it to be the derivative. So we're actually going to use that derivative notation, and you're saying, but this is my graph, you said only give us a number. I know, but we're going to outsmart it. So this is still going to be taking the derivative with respect to x, and we want to take the derivative of my function here. Now you could just type in the function, but something that's super handy is to use the y bars. Has anyone used y bars before? Okay, this is a great mechanism. So hit bars, arrow over to y bars. We're dealing with functions, we're not in polars or parametrics, so just functions. And it lists y1 through y however many we have. We want to take the derivative of what we have in y1, so we're going to use y1. Now here it might seem silly to do that, but let's say that my function was something crazy, such as sine of 3x minus cosine of 2x all over 2x squared plus 1. That would be a long thing to have to retype within here. So by using the y bars, instead of retyping it on that, what the calculator does, it says, take the derivative of the function sitting right here. So you don't have to retype it back. Right? And then where you don't want to look at a specific point, we want to look at every single x value. So we're actually going to put there x. Okay, so what we're telling our calculator is, hey, I want you to graph the derivative of my function y1, but I want you to do it at every single x value. Now, if you try to do that on the home screen, it's not going to work. It's not going to spit back up the function, but it works because what the calculator is doing is saying, all right, I'm going to plug in 1. Plug in 1, find the derivative of it at 1. Okay, now plug in 2. And so it's doing all the hard work for you. You'll see sometimes it takes a little while for the calculator to graph it. All right, so we hit graph. Looky there, our derivative is indeed 1, just like we thought. All right, so we got that first one, pretty easy. Our derivative was 1. Now let's take a look at x squared. So go back up here, and y1 I want x squared. Not x negative first. Sometimes that updates bothers them. Okay, now notice this we can leave alone, right? Because now we've changed y1, and since it's pulling y1, we don't have to actually change anything here. But if you typed in the function, you have to rewrite that function there. So this is actually really nice. All right, so we hit graph. And first we see my x squared, and then it's going to graph to us our derivative. Now, as it's working on that, we can take a look and see, on the left-hand side, do I have slope that's negative or positive? Negative. And at 0, what is my slope? 0. And then as I go to the right, what is my slope? Positive. And if we look, negative slopes, negative y values, 0, positive y values. So what type of graph is my derivative? It's a line. So we know it's some type of x. Now, if you take a look, can we figure out what that slope is? It's a y-intercept of 0. What does it look like our slope is? Yeah, it's 2. So our derivative here is actually 2x. Okay. So now let's take a look at x cubed. And I'm just going to change this. Cubed. Graph. And there's my x cubed. And already I should be able to tell positive slopes hits 0, so I should expect positive hits 0, and then still more positive slopes, so I should see positive. Ah, looky there. Positive value, 0, positive. And again, big positive, smaller positive, big positive, down to smaller, and likewise. What type of graph is that? It's a parabola, so we know it's going to be an x squared. It has been shifted left, right, or up or down, so it's centered at 0, 0. Can you guys identify what that a value is supposed to be in front though? So if we look, normally we go over 1, up 1, but here it was over 1, up 1, 2, 3, looks like. Alright, so my derivative here is 3x squared. Alright, and then let's do one more with x to the 4th. So again, we're going to go to y equals x to the 4th. Again, this is still taking the derivative of that first one with respect to x. Correct? Here's my x to the 4th, very similar to x squared. Again, we see negative slope, so I should expect it down to negative. Slope of 0, positive slope, so I should expect it to be there. Oh look, negative, 0, positive. Now this one, what type of graph does this look like? X cubed, good. Now I'm going to go ahead and give you that coefficient because it's not so easy to see. It ends up being 4. Okay. Now we can continue on like this for forever. Just real quick, just to make sure we all know this, we do know that we can change the thickness of our lines, right? Also, there's that I like the one with the circle. Because sometimes you think that it hasn't graphed, but what it actually graphed was right on that line x equals or y equals 0. So the thicker is easier to see, but this one here, what it does is it draws the line, and as it draws it, it uses kind of that 0. Maybe. Oh, I didn't actually change it. But that I think is nice because sometimes also too you might have that you're graphing the same function that you had already graphed, and you might not realize it, but as it draws it has a little 0 or little circle so you can see where it's actually going. So I think that's okay. Anyway, back to our derivatives. So we could continue in this pattern, seeing each one, but this kind of helps us to see the pattern here. What do we notice about the relationship between my powers for my original function and the derivative? Yeah. The exponent goes down 1. Here my exponent was 1. An exponent of 0, what's x to 0's power? Just 1, right? Here my exponent was 2, it went down to 1. Here it was 3, went down to 2. 4 went down to 3. Good, so we see that with our powers, the power drops 1. Now, a little bit harder to see is perhaps this coefficient in front. I know some of you guys already know how this gets there, but look at the relationship between your original's exponent and what your derivative's coefficient is. Notice my original exponent was 2, my coefficient of the derivative is 2. Original exponent 3, coefficient is 3. Original 4, coefficient 4. So what we have for our power rule is that when I have a function raised to a power, I take that power and I drop it down in front, and I take the power and reduce it by 1. So I multiply whatever that power is, that now becomes my coefficient in front, and then I take my power and reduce it by 1. So with this, we should be able to find the derivative of even something crazy such as f of x equal to 13x to the 5th power. What would my derivative be? 5 times 13x to the 4th. Well, we could simplify that. Hey, we're in Unit 2 now. So you've now entered into the world where you no longer have to simplify your answers. On the AP exam, if they were to ask you on a free response some question like this, which they won't because that's too easy of a question, that'd be more likely to be multiple choice. But if they were to ask you a question like this, you can leave your answer as 5 times 13x to the 4th. You don't have to actually multiply it out. And this is super helpful when on free response you start plugging in numbers and it's some crazy big expression that you have to simplify. You don't actually have to simplify. You plug in the numbers and then you leave it. Now you do have to evaluate trig. So if you're plugging in like 5 or 6, you do have to evaluate any trig that's in there, but you don't have to simplify. You don't have to do the arithmetic. And we will continue like that with our quizzes and our tests. You don't have to simplify your answers. And in fact, as much as this goes against every fiber of my being, I don't want you to simplify your answers. Because what happens to most students on the AP exam that decide they're going to simplify, they simplify it wrong because they did their arithmetic wrong, and then they get it wrong and they lose the point. Even if you had the answer correct at first, as long as you simplify whatever you keep working on, that's the answer that's created. So as we're doing problems on quizzes and tests, I want you to literally, once you plug in the numbers, stop and box your answer. I will go through and check every tiny minuscule piece. It takes forever, but it's for your benefit. Because on the AP exam, the graders will go through and grade every single piece. But if you decide you're going to go ahead and square that -3 and you put -9 rather than +9, your answer is wrong. Okay? So we're going to actually practice not simplifying, which feels very weird. Which means with that, you no longer have to rationalize the denominator. Okay? That's my gift to you. But I don't like giving that gift to you because I feel like it's bad to not simplify. But it's good for the AP exam, so we'll practice in that fashion. Okay, questions with the power rule? Okay. So now let's take a look at our sum and difference rule. No, actually, it's not different. So next is our sum and difference rule. And we're going to group it together because it's basically the same concept, just one's addition, one's subtraction. Now the disclaimer with this is that we're working with functions f and g that are differentiable, meaning that we can't take the derivative. So if I have the derivative of 2 functions added together, so again, d dx, and you can take the derivative of whatever these 2 functions add together, take the derivative of that. That is the same thing as the derivative of the first plus the derivative of the second. Okay, so derivative of the first plus derivative of the second. Pretty basic. Kind of similar to our limit rules there. Now this is the same for difference. If it is f of x minus g of x, then it's f prime of x minus g prime of x. Okay, so same rule for difference. So let's go ahead and apply these first few rules and do a couple of problems here. Let's go with I take it back. I want to do one more before we do that rule. I want to talk about our coefficient. Okay. So we also have our coefficient rule, which you might have already guessed, but we technically used it with our example previously. So we have our coefficient rule. It says if I take a derivative with respect to x, where I have a function and a coefficient multiplied in front, so c times f of x, or c is just some real number, so it could be like 5 times some function, 5 tangent of x, 5 times e dx, 5 times x squared. Then this is the same thing as the coefficient times the derivative. So really, you take the derivative and just leave your coefficient multiplied in front. We technically did that with our 13x. Okay, so again, we did that over here. 13x, we brought the 5 down, and so what you would do is multiply those together. Okay, so the 13 is my coefficient, so 13 times 5x. Alright, so now let's go ahead and do an example that kind of has all of these together. Combines our power rule with our sum of difference rule, coefficient, constant, all of that. Let's see. Let's go to this guy. Alright, so let's say f of x is 5x to the 7th minus 2x cubed plus 8x plus 1. Okay, so 5x to the 7th minus 2x cubed plus 8x plus 1. Let's go and find that derivative. So f prime of x, and make sure when you do that derivative, you label it as f prime of x. If you just say equals, then what you're doing is saying that this function equals what you're about to write, and that's not true because you're saying the function equals its derivative, and it's not true for this case. So make sure you label properly. All right, what is the derivative of this first piece here? Good. So again, so our 5 here is our coefficient, so I'm going to leave them there. And then my derivative, if I take here, remember we dropped that 7 in front, x to the 6th power. So again, my 5 is that coefficient, so I'm going to keep them in front. I then, for x to the 7, drop my 7 and reduce my power by 1. Are we good with that one? Now next here we have minus 2x to the 3rd. So again, I keep that coefficient. And what's the derivative of x cubed? Good. So we bring down that 3 and drop the power by 1. And next I have plus 8x. So I have plus that coefficient 8 times, what's the derivative of x? 1. And then what is my derivative of 1? 0. You don't have to write that in, I'm just going to write it in for this sake. So you could leave your answer like that on the exam. It's okay though to not have that 0, but let's just go ahead and simplify. What do we get here? 35x to the 6th. Negative 6x squared plus 2. Alright, so this is my derivative. Now, I don't expect you to do this step in between. I trust that you can drop that 7 and multiply it in your head, right? I trust you can drop that 3 and multiply with the negative 2 in your head. I don't expect to see every single little step like that, but that's where it's coming from. Questions with that? You don't. You could leave it like that. That would be fine. But honestly, you're probably going to want, because if I ask you to find f prime of 3, it's going to be 3. Yes? No, as long as you established it here, you could have stopped at that. I like to, in my final answer, re-label it. It's just good practice to do. Other questions on that? Oh, I would naturally be doing this. Yeah, it's okay to simplify like this stuff. I would be simplifying that because that's yeah. But when we start to get into problems, like you really might have something like this. That is what I don't want you to simplify in the AP exam or my exams. Leave it like that because you will probably mess up something with it. Yeah. Other questions? Yes. Okay. All right, so let's again just kind of recap before we move on, and let's use our highlighters / color pencils to bring out the important stuff here. All right, so constant. The derivative of any constant is 0. Okay. Power rule. Whenever we have a power, we drop that in front, and then we reduce my power by 1. It's another biggie. And again, these are the rules that we'll be applying throughout the whole year. We're just doing it with polynomials right now. So we've got constant, we've got our power. All right, sum and difference rule. Again, the derivative of the sum is just the derivative of each individual one added together. Okay, and then our coefficient. He just hangs out in front. These are the basic, really easy ones where you're like, I don't understand why people always say calculus is hard. Don't worry. We'll get there. Okay, so before we move on, questions with any of those? Those are like the easiest rules in calculus. Okay, so now let's take a look at the easy portion here. We're not actually going to do chain rule today. Oh, we're doing chain rule, just not today. No, it's the best one. That's like the fun one. It's challenging. You just have to be careful you don't get carried away with constant. That's why. Okay, so now we've been dealing with these with only exponents that were integers, right? We dealt with exponents of 5 and exponent of 3 and 7, but what about an exponent of 1/2? What about an exponent of negative 2/3? What do we do with that? What about the square root of x? Alright, so let's take a look at it with negative and rational exponents. What does that mean, rational exponent? Rational, good, that's back to algebra 2 there. Negative and rational exponents. How do we handle that? If I have f of x is equal to the square root of x, how do I find the derivative? Or if I have, let's go, we've been doing f of x this whole time, let's do h of x. If I have h of x is, I don't know, let's just go to like 1 over x cubed. How do I find my derivative there? Oh, h prime. What do we do with that? Okay, so with these scenarios, what you want to do is convert it to an exponent, whether with a rational exponent or a negative exponent. So for this first one, how could I rewrite this as an exponent? Okay, so the 1/2. Then we just use the same rules as we were doing before. There are no changes when our exponents are fractions or when they're negative numbers. So we do the same thing. I see power rule here, so I bring down my 1/2. And then I reduce my power by 1. What is 1/2 minus 1? Negative 1. And there's my proof. Now again, if this was your question on a test, you could just leave it like that. You need to be familiar though with being able to recognize this is the same thing as 1 over 2. This goes to my denominator. These are equivalent. Because what AP exam does to counteract that fact that you don't have to simplify is that on their multiple choice questions, their answers are not going to be the long crazy thing. It will be the simplified answer. Or it might be even a manipulation of this. Instead of having this as their answer, they might have that as their answer. So they're testing whether or not you know your algebra through those types of questions. Okay? But again, either one of these would be acceptable. Questions on that? Okay. Now how can I rewrite h of x here? That's the negative third. And again, we treat it just like normal. So go ahead and try this one on your own. Yeah, you still subtract 1 from the power. Yep. Alright, so did we get negative 3x to the negative 4? Very good. And again, you need to be able to recognize that this is the same thing as negative 3 over x to the 4. Okay. So the only slightly confusing thing with this is that when we were dealing with our positive exponents, we saw that numbers decrease in value, right? And here they're technically are getting smaller, but what that means in negative world is that the numbers are getting larger in the negative world. Okay. All right, so I'm going to give you a slightly more complicated one. Let's go with g of x. You need to really branch out to the other parts of the alphabet. All right, let's say that g of x is 5 over x cubed minus 2 over x squared plus x to the 1/2 minus 1 over x to the 1/3. 5 over x cubed minus 2 over x squared plus x to the 1/2 minus 1 over x to the 1/3. Take the derivative of that.
You were, I think it's like this is not powerful. So this would be minus x to the negative, or negative indicates that it was a fraction equals.
All right, go and compare your answer real quick with someone nearby you. See if you have the same thing. Check your signs. Alright, let's go and bring it back up front. Did we get negative?
Oh, minus 3 minus.
Alright guys, back up front please. Did we get negative 15x and negative 4? And this one, ooh, gets a little tricky. Positive 4x and negative third. Good. It's got to be that positive because when we bring down that negative 2, negative times negative is positive. Alright, and then we've got plus 1/2 x and negative 1/2. We agree there? And then here, again, negative indicates that it was in the denominator. Fraction indicates it's a radical. Okay, so this this converted to x to the negative 1/3. Okay, so then we get plus 1/3 x to the negative 4/3. Do we agree? Yep. Awesome. Give me thumbs up, thumbs down. How you do with that? Okay. Those of us that mess it up, do we see what our mistakes were?
Do we need to simplify?
Nope, that's good. If you really truly wanted to put it in the, like, change your exponents, that's fine. But you don't have to. All right. So now we're going to move on to what I find to be the more exciting part of today. Product rule and quotient, right? We talked about a number in front, we talked about a number by itself, we talked about powers, we talked about adding, subtracting. Where's the multiplying and dividing? Here it comes. All right, so let's start off with the product rule. Alright, so product rule is when we try to take the derivative of two functions multiplied together. So the derivative of f of x times g of x. So the derivative of f of x times g of x. Okay. Now, unfortunately, this is not just f prime of x times g prime of x. There's more to it than that. Right? So essentially what we do is we have to take the first derivative times, I already messed up. Take the first function times the derivative of the second, plus the second times the derivative first. That's what we do. Let's write it out. So first function times derivative of the other, g prime of x. So we multiply it. And then you just do it the other way. So plus g of x now stays the same times the derivative of f of x. So really what it is if you notice here, we have the original functions for each of them and the derivative for each of them. And they're matched up with the other guy. Now since this is all just addition and multiplication, remember it's commutative property. I could have done g prime of x times f of x, right? That's the same thing. And f prime of x times g of x. I could have also, flip-flop these. I could have started off and said g of x times f prime of x. What do I think it's? Nope, we're good. Okay. I could have done g prime of x, f of x, and then f prime of x, g of x. So as long as you've got derivative and non-derivative, and then flip it around, you're good. Okay. Now, depending on different textbooks, different websites will use different notation. I like this notation where you use u and v. I think it looks simpler. So what this is the function u times the function v, taking the derivative of those. And so what it is it's just the first one itself, u, times the derivative of the second, dv. This represents derivative of v, plus v dv. I just feel like it's catchier, u dv plus v du. But whichever one you want to use to memorize it. Again, you need to have non-derivative with derivative, but flip it around, non with derivative. Questions on that? Okay, let's do an example. Alright, so let's say that our function, we'll say y equals x minus 1 times x squared minus 2x plus 3. X minus 1 times x squared minus 2x plus 3. See how it's two different functions multiplied together. This is my first function, x minus 1. That quantity times my second function here. Now, if we didn't know our product rule yet, we could have actually just multiplied this all out, got some crazy long polynomial, and then just use the rules that we knew. That is definitely something you can do. It's just going to take longer. The product rule allows us to not have to do that. Okay. So let's go ahead and use this product. So you could either say dy dx, right? That means derivative. Or we could have said y prime. Because my function is labeled y, that's why we can use either of those. Okay, so just reminder notation. Okay, so we're going to leave, and let's see. The first stays alone, stays the same, just the first function by itself. So just x minus 1. And if I left that alone, I must do the derivative of the second. So now I'm doing the derivative of just this piece here. So derivative would be 2x minus 2. Unless it's specifically asked for. Okay, so again, I left the first alone. It just came straight down. I took the derivative of the second. Now, let's reverse the order. So plus, the second stays the same. And now we do the derivative of the first. What is the derivative of the first one? You don't even have to write that one if you don't want to. Okay, that's our answer. We're done. Now, if it requests that you multiply it all out, then you must. And in some problems, they'll create the problem in such a way that you will need to multiply it out. For example, if they asked you to find the third derivative of this, which means you have to take the derivative again and then again, it's probably in your best interest to go and multiply it out at that point and not have to do product rule within product rule within product rule. Okay, so again, first stay the same, derivative of the second. Second stay the same, derivative of the first. U dv plus v du. Questions on that? Okay. So now let's take a look at quotient. The more complicated ones, still not too bad, but you do have to commit some space in your memory to this. Okay, so we have our quotient rule. And quotient indicates what type of operator? Division. Okay, so we take the derivative of two functions being divided. Now again, the disclaimer anytime that we're doing dividing, make sure that whatever your function is in the denominator is not zero at that point that you might be investigating. And again, this is unfortunately not just derivative of the top divided by derivative of the bottom. It's a more complicated formula. Alright. So for this, you want to start off in your denominator. So we take the bottom, leave it alone, multiply it by the derivative of the top. So if you would, second stays the same, derivative of the first. And then it's minus. And then, again, you just reverse the order. So now top stays the same, times derivative of the bottom. So again, bottom times root of the top minus top times root of the bottom. And then in our denominator, it's kind of weird, it's just the bottom squared. Okay. So again, in my numerator there, I have bottom times root of the top minus top times root of the bottom over bottom squared. I think it looks easier using our u's and v's. So again, if I have u over v, take the derivative of that, then it's v du minus u dv over v squared. So v du minus u dv over v squared. Again, whichever method you want to use to help you out, it's really just memorizing that pattern. Now, you might also, if you use different resources, if you watch different videos, you might hear someone say low d high minus high d low over low squared. What they're saying is low d high means take the derivative of the top minus high d low take the derivative over low squared. That's another one that people say.
When you use the expression dy dx,
so d dx means take the derivative of this function, whatever comes after it, with respect to x. dy dx is saying take the derivative of y with respect to x. So if I have my functions labeled y equals, then I'd say dy dx, or I could say d dx of y. Does that make sense? Difference? But d dx means second derivative of whatever function I'm about to specify to you. Okay. Other questions on that? Okay. Now something I want you to notice here. I'm going to go side by side with this. Is that you could actually, since my product rule here is addition, we could use commutative property. And if you want, you could memorize this the other way around, right? I could redo this. I could say d du, so second times derivative of first, plus u dv. Right? Instead of going first times derivative of second, I could do second times derivative of first, first times derivative of second. And then that kind of matches up with your numerator over here. The only thing that changes is that sign. So I've had students in your class, they memorize it that way, where the product rule, you'll see in textbooks the product rule is presented like this. But since it is just addition, the commutative property applies. You can memorize as second times derivative of first plus first times derivative of second. And then over here, it's second times derivative of first minus first times derivative of second. It maintains that order. Okay, so if you'd like to do that, you're more than welcome. All right, let's just go and do a quick one with quotient rule. We'll get you out here. All right. All right, let's go ahead and do y equals 2x to the fourth minus 1 over x squared. And let's find our derivative. Okay. So 2x to the fourth minus 1 over x squared. So again, we start off in the bottom. Bottom stays the same, times derivative of the top. My derivative of the numerator here, 8x cubed. Okay. Minus, now we flip the order. Top stays the same. So make sure you use parentheses for that. Times derivative of the bottom. What's the derivative of the bottom next? 2x. All over the bottom squared. And again, if you did x to the fourth, that's fine. And then we're going to leave it like that. Okay, so again, bottom times derivative of the top minus top times derivative of the bottom over bottom squared. Product rule. Again, if you want to memorize it that way, second times derivative of first, first times derivative of second. Any questions on that? Okay. Now, I do want to show you one more here with product rule, in which it might not be easier to use product rule, but easier to use polynomials. Say that I have the example 3x squared times 10x to the fourth. Could we do product rule with that? Yes. Two quantities multiplied together. What would be another thing that we could do before we even take the derivative? Just multiply it out. What would this become? 30 x to the 6. And then can we do power rule pretty quick with that? So when you have that quantity where there's some adding, subtracting, that probably is going to be faster to do product rule. But if it's just something you can simplify real quick, it's probably easier to simplify and then do both. All right. Your homework is worksheet 2 on tracking these derivative rules. You might need a separate sheet of paper for a few of the problems, but most of them you can probably just fit directly onto the paper. Also, keep in mind that first part of your trig lab, when is that due? Next week, sometime the dates are the dates on that. So remember, I want your description of your route, your data table of the values, as well as your graph.
What time are you ready?
We need
It'll take like 40 minutes. I know.
I did pushing this to
Did anyone not get the homework? Alright, so again, make sure you start working that trip lab chart, description of where you go, and your own personal graph for what's to that first deadline.